Okay, in the lesson today, I'm going to focus on one of the main circuit applications for the Laplace transform. And I've elected to look at the AC series RL circuit. So we're going to solve this problem together. In a series RL circuit, the resistance is 4 ohms, the inductance is 20 millihenries, and the voltage is given by 80 times the sine of 400t. We're going to determine an expression for the current given that the initial current is 0. Hint, we will begin with Kirchhoffs voltage law to establish the relevant first-order differential equation, and then we'll use Laplace transforms to determine the current as a function of time. Okay, there's an important note here. So our independent variable will be time, and our dependent variable will be current. So this means that the formula we're accustomed to for the Laplace transform of y prime can be changed to this one, where we have the Laplace transform of I prime is S times the Laplace transform of I minus I at 0. And here I at 0 will refer to the initial current. Further, the Laplace table, which generally compares f at s with little f at t, will now compare capital F at s with little I at t. Okay, so again, we're going to solve this problem right here. And I'll begin in just a minute. I have to grab our table. Okay, so our very first step then is to start with Kirchhoffs Law. And this will be something that you remember from our previous unit. Okay, so we have a resistor and an inductor in series with the source. So Kirchhoffs law would look like this. We will have VL plus VR is equal to E. And we remember the formula for VL is L times I prime. And for the voltage across the resistor, we just use Ohm's law, which is current times resistance. So R times I. Okay, so here is the equation that we will use, and we can now substitute 20 milli, 4, and 80 sine of 400t. Okay, so 20 milli times I prime plus 4 times I is 80 times the sine of 400t. Now that we have the correct first order differential equation, in order to solve it, we will take the Laplace transform of each and every term. So that will look like this. Okay, so we took the Laplace transform of each term. Now right here, for the Laplace transform of I prime, of course, we're going to use the formula. So in this spot right here, I will put in S times the Laplace transform of I minus I at 0. Okay, so because it's a binomial, I should bracket that. Okay. Now, I at 0, however, means the initial current value. And in this problem, we're told that that initial current value is 0. So it's S times the Laplace transform of I minus 0. So this term now will just look like this. Okay? Because again, this term is 0. Now, on our right side here, after 80, so 80 remains as a multiplier, what I need to do is write down what the Laplace transform of the sine of 400t is. So we use our table and we find that we can use transform number 6 with a equal to 400. So we're going to have 400 over s squared plus 400 squared. And again, the 80 remains as a multiplier. So it's like having 80 times 400 in the numerator, which means having 32,000 in the numerator. Okay, so I can write the right side in this way. All right, now remember our objective is to isolate the Laplace transform of I. So that means we common factor it from the left side, and when we do that, in our bracket we will have 20 milli times s plus 4, just like that. Continue to isolate the Laplace transform of I. So what does this mean? It means dividing by 0.02 s plus 4. All right, just like that. Now at this point, you would start thinking about your table. Now one thing is perfectly clear. In the table, any term looking like this would have a coefficient here of 1, okay? So we cannot keep this coefficient of 0.02. So what does that mean? That means we need to change this term by dividing by 0.02. So both of these numbers get divided by 0.02. You will not be changing this term here, okay? So we're gonna get s plus, and now again, you have to do 4 divided by 0.02, and you'll find that that's 200. Okay, so in moving from this denominator to this denominator, we have divided the denominator by 0.02. This means we have to divide the numerator by 0.02 also. So you can take 32,000 and divide it by 20 milli. You'll find that it's 1.6 million or 1.6 mega. Okay, so again, in moving from this step to this step, we simply divided the denominator by 0.02, and then we had to divide the numerator also by 0.02. Make sure that you don't do anything to the other term in the denominator, or the effect would multiply, right? All right, so this is correct now. And so we look for this denominator in our chart, but you will quickly find that it isn't there. This is like an s plus a term. This one's like an s squared plus a squared term. And nowhere do we have both of those in one single denominator. Okay, so what does that mean? It means we're going to have to split this using partial fractions. Okay, so here we go. Here's the original fraction. And we are changing the original fraction so that it will be the sum of two fractions, one with a denominator of s plus 200 and the other with a denominator of s squared plus 400 squared. And of course, we have to correctly set up the numerators. Because this is s plus 200, sorry, s plus 200. Okay, because this is a linear term, we require only a single letter in the numerator. But this term is quadratic. Okay, so in the numerator, we require something linear. In other words, something of the form b times s plus c. Okay, so now we write out our large equation. So we take the original numerator and we set it equal to a multiplied by s squared plus 400 squared plus bs plus c, which must be in a bracket because it's a binomial. It is multiplied by s plus 200. And our job now, of course, is to solve for the values of a, b, and c. Do we have any roots we can use? The only root is s equals negative 200. So we begin with that. We substitute s equals negative 200. Now, when that is substituted into the left-hand side, nothing changes. When it's substituted into the right-hand side, this bracket becomes negative 200 all squared plus 400 squared. And of course, negative 200 all squared is a positive number. Okay, it's the same as 200 squared plus 400 squared. So this number is 200,000. And so A is 1.6 million divided by 200,000. A is equal to 8. All right, that's the only root. Okay, there is no s value such that s squared plus 400 squared is 0. So that's the only root. So it's too early to substitute an arbitrary s value. So we have to use coefficients, and often using the highest coefficient will work. So here that would be the coefficient of s squared. There is no s squared term on the left side, so we write 0s squared equals, where are the squared terms on the right side? Here, as squared plus, and then here, bs squared. So we find that 0 is a plus b, and since a is equal to 8, we then have 0 is 8 plus b, from which b is found to be negative 8. Okay, finally, we can use a coefficient to figure out c. For example, I could use the coefficient of s. If I don't like that, I can substitute an arbitrary s value. For example, substitution of s equals 0. So either of those ways would work. If you use the coefficient of s, you would write 0s is 200bs plus cs, like this, okay? 0s is equal to, So there is no s term here, but there are two in here from the outside and the inside. So on the outside, it would be 200b times s. And there would be a second one after the plus sign on the inside, c times s. Okay, from which we get this equation. 200b plus c is 0. And b, remember, is -8. So this is 200 times -8. So that's -1600, from which c is 1600. Okay, so that's one way to solve for c. The other way would be, instead of including any of this, just substitute s equals 0 throughout the equation, and you would also be able to determine that c is 1600. Okay, now I have my three values, so I'm going to just pop them into this right-hand side here. So that will look like this. We'll have the Laplace transform of I is equal to 8 over s plus 200 plus, now it's bs plus c right here. Is that on the screen or not? Yeah, just. So bs plus c, which is -8s plus 1600. And that's with the s squared plus 400 squared under it, like that. Okay, so now we go to our table, hoping to find these denominators and then the numerators. So starting with this one, I think you're very accustomed to this one here. This is just number 3. The 8 can be moved out front. Where's this denominator? S squared plus a squared. Okay, I think that you can see it's here and here. But with one of them, we have an S in the top. With the other, we have a number in the top. So that would suggest that I break this now into 2. Okay, so I will have minus 8s over s squared plus 400 squared, and then plus 1600 over s squared plus 400 squared. Let me just put in these division lines here. Okay, so see what we did? It was -8s, it still is -8s, positive 1600, and it still is. Same denominator. Because, of course, if you carried out this operation, you could combine them since they have like denominators. So now we're going to try to use transforms 3, 5, and 6 respectively. But here we're going to move the 8. Here we're going to move the 8. This one, we should have whatever A is up top. Well, A is 400. So this should be 400 here, not 1600. Okay, so let's fix this. So the 8 can move to the front. Right? Same thing here. The -8 can move to the front. Like that. Those two are very easy to handle. But you know what? So is this last one. We want to leave 400 on top. Okay, because then we would have A over S squared plus A squared. But this is 1600, and now suddenly it's only 400. Well, that doesn't work, but we can do that because 4 times 400 is 1600, right? All you have to do is make sure that what you write in this line is exactly what you've written here. So 8 times 1, yes. -8 times S, yeah. 4 times 400. Okay, so this is all good. Now here we go. We're at the step where we write current is, and we're going to have 8 times something minus 8 times something else plus 4 times one more thing. And we're using transforms 3 and 5 and 6. Okay, so let's make sure we do this correctly. So here we have A is 200, so this becomes e to the negative 200t. And here we have A is 400, so this is cos 400t. And lastly, after the coefficient of 4, we have A is 400. This becomes the sine of 400t. And we're now finished the problem. This is the expression for current for our circuit. All right? All right, so what I would love is for you guys to try from your exercises 3112, number 30 and number 35. I've provided you with the final answer for 30 here, since that's not included at the back of your textbook. But try those two problems, okay? And I can post solutions for those for you as well. Okay, thanks so much. Have a good day. And as I said, this is one small example. There are second order differential equations that are circuit applications also. For example, you can, since we could consider, for example, an equation for a charge, right? So if you wanted an equation for charge and you were using a circuit containing both an inductor and a capacitor, that would be a second order differential equation that can be solved using Laplace transforms. So there are many, many possibilities. I've just focused on one for this math class, but Mr. Jankos will be doing many, many others with you as well. Okay, thanks. Have a good day.